January 17, 1940. Cambridge, England. The winter wind cuts through the narrow corridors of the Cavendish laboratory like a blade. Inside room 14, a man named Henry Boot stands before a copper cylinder no larger than a fist, its surface still warm from the lathe. The metal gleams under the weak laboratory light. Outside, the war is 6 months old. France still stands. The Blitz has not yet begun. But here in this cold room that smells of machine oil and solder, a physicist stares at a piece of copper and wonders if it might be the thing that saves civilization. He does not know it yet, but he is holding the future. The cavity magnetron. A device so small a child could palm it. A device that will make the invisible visible, that will turn darkness into light, that will allow men to see through storms and fog and the black curtain of night itself. In the months to come, German U-boat captains will surface in the Atlantic and find Allied destroyers waiting, impossibly, as if summoned by sorcery. Luftwaffe bomber pilots will turn back from their missions, unnerved by the uncanny accuracy of British night fighters that appear from nowhere. Japanese naval commanders will watch their fleets dissolve under air attacks guided by eyes that should not exist. And all of it will trace back to this moment, to this copper cylinder, to this one man's insane idea about how to make microwaves dance. But first, we must understand what they were fighting against. In 1940, radar was not new. The British had it. The Germans had it. Even the Americans were experimenting with it. The principle was simple enough. Send out a radio wave, wait for it to bounce back from an object, measure the time, calculate the distance. It was the electronic equivalent of shouting into a canyon and listening for the echo, but there was a problem, and it was fundamental. The radar systems of 1940 operated on long wavelengths, meters, not centimeters. This meant their antennas were enormous, their resolution was poor, and their ability to detect small objects was nearly non-existent. A British chain-home radar station could detect a formation of German bombers approaching across the channel, yes, but only as a vague blob on a cathode ray screen. It could not tell you how many aircraft. It could not distinguish a bomber from a fighter. It could not guide a night interceptor to within firing range, and it certainly could not be mounted on an aircraft itself. The transmitters were the size of refrigerators, powered by vacuum tubes that consumed kilowatts and generated wavelengths measured in meters. What the Allies needed was microwave radar, wavelengths measured in centimeters. Shorter wavelengths meant smaller antennas, sharper resolution, the ability to see individual aircraft, even individual ships. Microwave radar could be mounted in the nose of a bomber or beneath the belly of a patrol aircraft. It could detect a submarine's periscope cutting through the Atlantic swell. It could guide a bomb to a target through total darkness. It could, in short, change everything. But in 1940, no one knew how to make a microwave transmitter powerful enough to be useful. The Germans knew this. Their scientists had explored the problem and concluded it was insoluble with current technology. The vacuum tubes required to generate microwaves at useful power levels would be impossibly complex, impossibly fragile. The Reichsluftfahrtministerium filed the research away. Microwave radar was a theoretical curiosity, nothing more. The British, facing extinction, decided to try anyway. Henry Boot was not supposed to be a hero. He was 32 years old, a physicist with a specialty in resonant cavities, the kind of esoteric research that produces 3 readers for every published paper. He worked at the University of Birmingham under Professor Marcus Oliphant, an Australian with a voice like gravel and a temperament to match. Oliphant had been tasked by the government's Committee for the Scientific Survey of Air Defence to investigate whether microwave radar was possible. The answer, according to every previous attempt, was no. But Oliphant was not interested in previous attempts. He assigned Boot and another physicist, John Randall, to solve the problem. Their resources were absurd. A small laboratory, a modest budget, and 6 months. No pressure. Just invent a device that does not exist to solve a problem everyone else has given up on, while your country prepares for invasion. Boot and Randall began with the Magnetron, a device invented in 1921 by American physicist Albert Hull. The original magnetron was simple: a vacuum tube with a cathode at the center and an anode surrounding it. Apply a magnetic field perpendicular to the electric field, and electrons would spiral outward in graceful curves, generating oscillating currents, radio waves. But Hull's magnetron was weak. It could barely power a light bulb, let alone a radar set. The problem was resonance. To generate high-power microwaves, you needed the electrons to oscillate at exactly the right frequency, and to do that, you needed a resonant cavity, a precisely shaped chamber where electromagnetic waves could bounce back and forth, building in intensity like a note sustained in an organ pipe. But integrating resonant cavities into a magnetron was considered impossible. The geometry was too complex. The engineering tolerances were too tight. Boat looked at the problem differently. What if the anode itself was the resonant cavity? It was insane. It was elegant. It was so simple that everyone had missed it. He took a solid copper cylinder and drilled holes into it. 8 cylindrical cavities arranged in a circle around the central cathode. Each cavity was a resonator, tuned to the exact frequency of the microwaves they wanted to produce. When electrons spiraled outward from the cathode, they would pass by the openings of these cavities, inducing oscillations. Those oscillations would feed back into the electron stream, bunching the electrons into clouds that rotated around the cathode like a pinwheel. The bunched electrons would induce stronger oscillations. The stronger oscillations would bunch the electrons tighter. It was a feedback loop, a runaway amplification effect that would generate microwaves at extraordinary power levels. In theory, Boot and Randall built their first prototype in February 1940. It was a crude thing, hand-machined from brass and copper, sealed with wax. They connected it to a power supply, activated the magnetic field, and watched the meters. The device produced 400 watts of microwave power at a wavelength of 9.8 centimeters. 400 watts. For context, the most advanced German microwave transmitter produced 0.1 watts. The best American effort produced 10 watts. Boot and Randall, in a basement laboratory in Birmingham, had just increased the state-of-the-art by a factor of 40. Oliphant stared at the readings and said nothing for a long moment. Then he picked up the telephone and called London. By August 1940, the Battle of Britain was underway. Luftwaffe bombers darkened the skies over England in formations of hundreds. RAF Fighter Command was bleeding pilots faster than it could train them. The Royal Navy was losing ships to U-boats at a rate that threatened starvation. Britain was alone, and it was losing. Winston Churchill made a decision. He would send Britain's most valuable military secrets to the United States, not as a bargaining chip but as a gift, a desperate plea for help. Among those secrets was the cavity magnetron. In September 1940, a British technical mission boarded a ship in Liverpool. They carried with them a single locked box. Inside that box was a cavity magnetron, wrapped in cloth, nestled in foam. Also inside were blueprints for proximity fuses, designs for jet engines, research on atomic fission, every strategic technology Britain possessed. If the ship was sunk by a U-boat, the war might end then and there. The ship was not sunk. On September 29th, the British mission arrived in Washington and requested a meeting with American military and scientific leaders. The Americans were skeptical. The British had a reputation for exaggerating their achievements. But when the box was opened and the magnetron was placed on the table, the room went silent. One American engineer, upon seeing the device demonstrated, said simply, "This is worth all the rest of the box combined." He was right. The United States immediately began mass production. The radiation laboratory was established at MIT with a singular mission: weaponize the magnetron. Within a year, American factories were producing thousands of cavity magnetrons per month. Within 2 years, microwave radar sets were standard equipment on Allied ships, aircraft, and ground installations. The Germans never caught up. German radar operators in 1941 knew the Allies had improved their systems. That much was obvious from the increased accuracy of British night fighters and anti-aircraft fire, but they assumed it was an incremental improvement, a refinement of existing long-wave technology. Their own scientists assured them that microwave radar was impractical. The Forschungsamt and the Telefunken engineers had done the calculations. High-power microwave generation required devices of such complexity that battlefield deployment was impossible. The Allies might have laboratory prototypes perhaps, but nothing operational. This was not arrogance. It was a reasonable extrapolation based on the best available science. German radar technology was among the finest in the world. Their Würzburg fire control radars guided flak batteries with lethal precision. Their Freya early warning systems stretched across occupied Europe in an electronic fence. They had every reason to believe they understood the state of the art. Then their U-boats started dying. In the Atlantic, submarine warfare had followed a predictable rhythm. A U-boat would surface at night to run its diesel engines and recharge batteries. In darkness, on the open ocean, it was nearly invisible. Allied patrol aircraft would pass overhead, blind, and the submarine would slip away. This was the gap that Admiral Dönitz exploited, the nighttime surface transit when his boats were safe. In early 1943, that safety vanished. U-boat captains began reporting impossible encounters. Allied aircraft appeared from nowhere in total darkness. Depth charges dropping before the alarm could even sound. Boats that surfaced at midnight and were dead by 12:15. The crews that survived spoke of the attacks with confusion bordering on superstition. How could the enemy see them? There was no moon, no stars. The sea and sky were one continuous black. Dönitz demanded answers. His intelligence officers interrogated survivors, analyzed attack patterns and studied wreckage. The conclusion was inescapable. The Allies had developed airborne radar that could detect a surfaced submarine from miles away. But how? The antennas on Allied aircraft were small, far too small for long-wave radar. The physics made no sense. Unless German naval intelligence eventually captured an intact Allied radar set from a downed aircraft. When their technicians opened the casing and saw the magnetron, they understood microwave radar, operating at 10 centimeters, small enough to fit in a bomber's nose, powerful enough to paint a surfaced U-boat on a scope like a full moon. The chief engineer who examined the device wrote in his report, "We are at least 2 years behind, and we have no clear path to catching up." 2 years. In submarine warfare, that was eternity. Captain Werner Henke commanded U-515, one of the most successful boats in the Kriegsmarine. Between 1942 and 1943, he sank over 30 Allied ships. He was careful, methodical, a hunter who understood that survival depended on invisibility. He surfaced only at night, only when the weather was foul, only when his instincts told him the sky was empty. On April 9, 1943, his instincts failed him. U-515 surfaced in the mid-Atlantic, 900 kilometers from the nearest land. The night was overcast, visibility near zero. Henke ordered battery charging to begin. Standard procedure. Around him, the watch crew scanned the darkness with binoculars, listening for the sound of aircraft engines. 12 minutes later, a British Wellington bomber descended from the cloud layer directly above them, dropped 4 depth charges, and was gone before the bridge crew could even man the deck gun. The charges detonated close enough to shatter gauges, spring leaks, knock men off their feet. Henke crash-dived. The boat survived, barely, limping away with a damaged pressure hull and a crew that would not stop shaking. Later, after the war, Henke would tell interrogators that this was the moment he understood Germany could not win, not because of production, not because of resources, but because the enemy could see in the dark, and Germany could not. It was like fighting a man with eyes when you have none. "We became prey," he said. This was the transformation. For 3 years, U-boat crews had been hunters, skilled, confident, masters of their domain. The Atlantic was their hunting ground, and Allied convoys were the game. Then, almost overnight, the equation reversed. The U-boats became the hunted. They crept through the ocean in terror, surfacing only when absolutely necessary, knowing that invisible eyes might be watching, that death could fall from a sky they could not see into. The statistics were brutal. In the first 4 months of 1943, before widespread deployment of microwave radar, the Allies lost 120 ships to U-boats. In the last 4 months of 1943, with microwave radar fully operational, they lost 30. The U-boat fleet, meanwhile, lost 75 boats in those final 4 months, a casualty rate of over 60%. By 1944, sailing in a U-boat was a near-certain death sentence. The German submariners knew why. They had a name for the Allied radar, Das Auge, the eye. In mess halls and torpedo rooms, they spoke of it in tones usually reserved for curses. Some boats carried primitive radar detectors, receivers that could pick up the microwave pulses and sound an alarm. But detection meant nothing. By the time the alarm sounded, the aircraft was already overhead, the bombs already falling. The eye saw everything, and there was nowhere to hide. If the cavity magnetron transformed submarine warfare, it revolutionized strategic bombing. In 1942, RAF Bomber Command faced a humiliating reality. Its bombers could not hit their targets. Night raids over Germany were flown blind, navigated by dead reckoning and hope. Bomber crews would drop their payloads on what they believed was a munitions factory or a rail yard, only to learn later that they had struck farmland 10 miles away. The inaccuracy was so severe that British operational research concluded less than 1/3 of bombs dropped fell within 5 miles of their intended target. 5 miles. The strategic bombing campaign, upon which Britain had staked enormous resources and countless lives, was essentially random. The solution was H-2S, an airborne ground mapping radar using cavity magnetrons. The name was reportedly chosen by a scientist who declared that the previous state of affairs was a hell of a stink, hence H-2S, the chemical formula for hydrogen sulfide. The device scanned the ground beneath the aircraft, painting a crude but recognizable image on a cathode ray screen. Cities appeared as bright blobs. Rivers were dark lines. Coastlines were unmistakable. A trained operator could navigate to a specific factory complex in total darkness, through clouds, in the face of jamming, and mark it with incendiaries for the following bomber stream. The first H-2S-equipped Pathfinder force flew on January 30, 1943, against Hamburg. The raid was devastatingly accurate. Subsequent raids on the Ruhr, on Berlin, on Cologne, all were guided by H-2S. The civilian population of German cities learned to fear the clear, high-pitched tone of the Pathfinder markers igniting, a sound that meant the firestorm was coming. German night fighter pilots, too, experienced the transformation. Before H-2S, they hunted Allied bombers by vector from ground controllers, guided toward the bomber stream by Himmelbett radar stations. It was a clumsy system, dependent on good weather and clear radio communication. Then Luftwaffe engineers discovered they could build receivers to detect H-2S transmissions. Suddenly, British bombers were beacons. German fighters equipped with Naxos radar detectors could home in on the H-2S signal from tens of miles away, turning the hunter into the hunted. But even this was not enough. The Allies produced magnetrons faster than Germany could build detectors. They varied frequencies, encrypted transmissions, saturated the electromagnetic spectrum with noise. The technological gap was not just a matter of years. It was a matter of industrial capacity. The United States alone produced over 1 million cavity magnetrons during the war. Germany produced, at best, a few thousand inferior copies. The race was over before it began. There is a symbolic power in the magnetron itself. The copper cylinder with its machined cavities, its elegant simplicity. It became a talisman of Allied technological superiority, passed from hand to hand, factory to factory, each unit identical to the last. German engineers who examined captured magnetrons were struck by how simple it was. No exotic materials, no fragile vacuum tubes requiring constant replacement, just copper, iron, and precision machining. It was a device that could be mass-produced by the tens of thousands, installed by a technician with basic training, and maintained in the field with simple tools. This was the genius of it. The magnetron was not a laboratory curiosity. It was a weapon designed for war, robust, reliable, reproducible. British and American factories stamped them out like rifle cartridges. By 1944, every Allied bomber, every patrol aircraft, every destroyer and escort carrier carried magnetron-based radar. It was ubiquitous, invisible, and utterly decisive. German soldiers, sailors, and airmen came to associate that copper cylinder with a deeper truth, that the Allies possessed not just better technology, but a better system for producing and deploying it. The magnetron was a symbol of industrial abundance, of a war machine that could outproduce and out-innovate anything the Axis could muster. A German radar operator captured in 1944 remarked to his interrogators that the most demoralizing thing about Allied radar was not its sophistication, but its omnipresence. You could destroy one set, he said, and there would be 10 more the next day. It was the mathematics of democracy, messy, inefficient, but inexhaustible. Japanese naval officers experienced their own reckoning with the magnetron, though they understood it less clearly. At the Battle of the Philippine Sea in June 1944, American carrier task forces detected and intercepted Japanese airstrikes at distances that should have been impossible. American fighter directors, guided by microwave radar, vectored Hellcats onto incoming Japanese formations with uncanny precision. The result was a massacre so one-sided that American pilots called it the Great Marianas Turkey Shoot. The Japanese lost over 600 aircraft in 2 days. The American losses numbered fewer than 30. Japanese commanders struggled to explain the defeat. Their pilots were experienced, their aircraft were adequate, their tactics were sound. Yet they had been slaughtered like livestock. Some attributed it to American numerical superiority, others to poor intelligence. But the truth was simpler and more devastating. The Americans could see them coming from 100 miles away, and the Japanese could not see the Americans at all. This was a psychological blow as much as a tactical one. The mystique of Japanese naval aviation, the idea that superior spirit could overcome material disadvantage, died in the skies over the Philippine Sea. Survivors returned to their carriers shaken, speaking not of enemy skill but of enemy omniscience. It was as if the Americans were playing with marked cards, as if they could read thoughts. In a sense, they could. Henry Boot lived until 1983. He never became famous. There were no parades, no monuments, no Hollywood films. He returned to his work in physics, published papers on electromagnetic resonance, supervised graduate students, and lived quietly in the English countryside. When asked about the magnetron, he would say only that he and Randall had been fortunate to work on an interesting problem at an important time. But in the decades after the war, the cavity magnetron became the foundation of an unexpected peacetime revolution. The same device that had hunted U-boats and guided bombers was adapted for a new purpose, heating food. In 1946, an American engineer named Percy Spencer noticed that a magnetron he was testing had melted a chocolate bar in his pocket. He experimented further, found that microwave radiation could cook food rapidly and efficiently, and filed a patent. By the 1970s, microwave ovens were in millions of homes. The device that had once made darkness visible now reheated leftovers. There is poetry in this. The magnetron was born from desperation, from the need to see an enemy that hid in night and fog. It was a tool of violence, designed to kill submarines and guide bombs. But its true legacy was illumination, not just the illumination of the battlefield, but the illumination of possibility. It proved that invention does not require vast resources or decades of research. Sometimes it requires only a small room, a clever mind, and the courage to try something insane. The magnetron was a piece of copper. It was a feedback loop of spiraling electrons. It was a physical manifestation of the idea that light can be conjured from darkness, that the invisible can be made visible, that even in the face of extinction, the human mind can find a way forward. When Boot stood in that cold laboratory in January 1940, holding his copper cylinder, he could not have imagined the world it would create. He could not have known that his device would sink hundreds of ships, guide thousands of bombers, save countless lives. He could not have foreseen the microwave ovens, the radar speed guns, the satellite communication systems, the air traffic control networks, all descendants of his insane idea about making microwaves dance in a cavity. He knew only that the problem was supposed to be impossible, and that he had solved it anyway. And perhaps that is the larger truth, the lesson that echoes across the decades. The Axis powers looked at microwave radar and concluded it could not be done. They were scientific, rational, realistic. They calculated the difficulties and decided the effort was not worth the cost. The Allies, desperate and besieged, decided to try anyway. They gave 2 physicists a basement laboratory and 6 months, and those 2 physicists handed them the future. This is the advantage of democracy, of systems that allow the insane ideas to be tested, that permit the impossible to be attempted. It is not that democracies are always right. It is that they are willing to be wrong in pursuit of something better. It is the freedom to experiment, to fail, to try again. It is the abundance that allows for risk. The Germans were brilliant. The Japanese were dedicated, but they were constrained by systems that could not tolerate the chaos of true innovation. They needed permission. They needed certainty. They needed the impossible to be possible before they would attempt it. Boat and Randall needed only a lathe, some copper, and the stubborn refusal to accept that seeing through darkness was impossible. That copper cylinder, no larger than a fist, carried within it the weight of a civilization. It was the concentrated essence of a way of thinking, a way of building, a way of being. It said, "We do not know if this will work, but we will try anyway." It said, "The night is dark, but we will make our own light." And in the end, they did. The cavity magnetron made the invisible visible. It turned night into day. It gave the Allies eyes when their enemies were blind. But more than that, it proved that freedom is not just a philosophy or a system of government, it is a practical advantage. It is the ability to take an insane idea from a physicist in a cold laboratory and turn it into 1,000,000 copper cylinders that change the world. Boat never claimed to be a hero. He never sought recognition. But every time you heat a cup of coffee in a microwave, every time a ship navigates by radar, every time an aircraft lands in fog, you are benefiting from a moment of desperation in a Birmingham laboratory, when one man looked at a piece of copper and decided to try something impossible. The magnetron won the war not because it was a weapon, but because it was a proof. It proved that seeing the truth is more powerful than any amount of darkness. It proved that the future belongs to those willing to illuminate it. And that light, once kindled, can never be extinguished.